Okay, so yesterday I talked about this operad which I denoted Cn, or we had C1 and C2 explicitly on the board. Cn, little n cubes. And these little n cubes, they are somehow also historically sort of the origin of the theory of operads. It's the most important occurrence in the early days. So in some sense is the mother of all operads. And there is even a notion derived from Cn, namely the notion of an En operad. And an En operad is an operad which is equivalent to Cn. So that's a bit of a philosophically a bit of a funny way of introducing a mathematical notion. You have an example and you say anything equivalent to the example, I give it a name. But the interesting thing is that
you didn't find equivalence between.
I'm aware. But it's just like yesterday. But the interesting thing is that these En operads come in many guises. So I will mention a few examples. There is the Fulton-McPherson operad, which is a specific compactification of configuration space, is extremely geometric in nature. There is a way of constructing En operads from categories with n distinct monoidal structures. And I'm not sure whether I will be able to be specific about this. What I would like to emphasize today is an operad in terms of graphs, complete graphs. Mm-hmm. And there is a fourth, which I will just call the McClure-Smith operad, McClure-Smith operad, which is based on the theory of co-simplicial, multi-simplicial spaces. Mm-hmm. So it uses, again, a different kind of combinatorics. And the strange thing is that in the literature, these things are compared, but there seem to be no correct, complete proofs in literature. So I tried to repair that with a student of mine, Boykelman. So we have a paper in the archive. It's called a Small Catalogue of En operads, and you will find detailed comparisons, hopefully correct comparisons between all these operads, and of course detailed definitions. So I will mainly concentrate on the complete graphs here today. And as we go along, I will also give a precise definition of what it means for two operads to be equivalent. Mm-hmm. Okay, so I will use a slightly different definition of operads from a more flexible definition compared to what I did yesterday. It's in literature it's called a coordinate-free approach. So an operad P assigns to each finite set a space or a category or a partially ordered set or a simplicial set P of A. Okay, so you should think of this as the operations that take an A-index family of inputs and spit out some output. And there are composition operations which I will write as PA. You pick an element in A and you substitute an operation with a B index family of inputs for this A, I call it circle little a, and it goes into P of the set A with the element A replaced by B. Okay, so it's this composition. You have an A index family, you pick a particular input A, and you substitute here B. So the leaves of this tree are A minus little a plus B. That's the notation for this set. I don't think it will occur very often, but I hope it's clear what I mean. And of course there are conditions, associativity, symmetry, and so on, that I'm not going to write down. So it's a coordinate-free definition of an operad. So this complete graphs operad is called G sub n in the paper. That's the same n as the dimension of the cubes here. And so I will begin by giving you a definition of Gn, of the operad Gn. And it's an operad in partially ordered sets. Both sets. Okay, so an object, so Gn of A for each set A is a poset. Okay, is the poset of complete, directed, weighted graphs on A vertices. Okay, that's a long sentence. So you have, what I mean is, you have a set of vertices, A primed, A double primed, and so on. Okay? And there will be further conditions, so if you're taking notes, leave some space. There will be a complete graph, so it will be between any two vertices there will be an edge. Okay? It will be directed, so it is complete as an undirected graph. It will be directed. I may write a non-example after I've put the condition. And it will be weighted, and it will be weighted by the numbers 1 up to n. Okay? Weighted by 1 up to n. So every edge in the graph has, as it were, two labels. One for a direction and one number, 1 up to n, the weight. Okay? And then there is one further condition. There are no cycles in the graph. No cycles. Okay? So what this means is that really the elements in the graph must form a linear order. Okay? So 1, 2, 1, for example, this would be an element of G, 2, 3. Okay? Now, so I hope that's clear. That's a relatively simple condition. But I haven't told you what the partial order is. Okay? So if so for G and H in Gn of H, Gn of A, say G less than or equal to H, whenever, now I'm putting the condition, I will say it in words first. So if you have an arrow in the graph, in the small graph, with a certain weight, then the weight has to go up in H, and it has to go up strictly if the direction is reversed. Okay, so whenever if A, I, B in G, then either A, J, B in H, and J is at least I, or A, J, B in H, but j must be strictly larger than I. Okay?
I don't know. So, can you give an example? So these are two weighted graph, two weighted graph with the same vertices.
Okay, so here is a graph. Okay? So this one is larger than A, 2, B,
The same vertices.
1, C, and then here I have a lower weight, and I change the direction.
Yeah, okay.
Okay? I don't have to change the direction, but I'm allowed to change the direction, but then I have to increase the weight, strictly. Okay? This is all for a fixed A.
Yes.
Okay? So for a fixed A, I've defined a partially ordered set.
On all the graphs, on the full graphs, on the weighted full graph. Yeah.
So once more, Gn of A is a partially ordered set. Its elements are completely directed weighted graphs with this specific set of vertices, with the condition that there are no cycles. Okay? And the partial order I've just explained. What I haven't explained yet is the operad structure. Okay? The operad structure is defined by replacing a vertex by a graph, and then, so operad structure replace a vertex by a graph. And do the obvious thing. Okay? So if you have if you have the map from GNA times GNB to GNA with A replaced by B, you pick your vertex named A, okay? And you replace this vertex by the graph which you had here. And this number 2 goes to all these vertices. Okay, so I will not write the formal definition. I hope it's intuitively clear. Yeah?
And it's still without cycles.
You can check it's without cycles. And you can check this is a map of posets. It preserves the partial order. All these things are easy to check, and I do not want to.
When you say that A is replaced by the set B, do you mean that you take out the element A and plug in this set B as an element?
Yeah.
Then why is it why the operation of A will still preserve the same property? Why have two directions which are meeting?
No, this everything is okay. Everything is okay. I said you have to check a few things, that you don't create cycles, for example. Yeah, I said it, yeah. I can check all these things for you if you like, but we will be here for 2 hours and have not done anything. So, okay, now this operad was defined in this way by Clemens Berger quite a while ago, and it was partly inspired by earlier work by Kashi Wabara, Japanese mathematician. And the relation to these little n cubes goes as follows. So there is a map be careful, I put it in quotes, from Cn of A to Gn of A. Okay? So initially people thought there was a map like this. And the map is very easy. The idea of the map is very easy. And now maybe I use the sideboard for this. So if you have a configuration of cubes, A, B, C, I'm going to produce a graph for you. Okay? The dimension is 2, so it's weighted by the numbers 1 and 2. Okay? So the graph will have vertices A, B, and C. And I'm going to put an arrow with a weight from... this is not going to be the arrow. Okay. So I'll put AIB if I is the first coordinate separating the A cube from the B cube with A before B in the I direction, in the I coordinate. Okay? So that's the idea. So let's look at this example. A comes before, A is separated from C. This is the first coordinate and this is the second coordinate. A is separated from C in the first coordinate. Okay? A comes completely before C in the first coordinates. So here I put a 1. A overlaps with B in the first coordinate. But they're disjoint cubes, so they have to be separated. So this one is separated in the second coordinate, but then B comes below A. So the arrow goes like this. Okay? And the same for C and B, the way I drew it. Okay? Slight problem, we have a cycle. So I chose this example on purpose. Okay? So there's almost a map. So however, it lands in the larger operad wait. Larger operad GNX where GNX A has no cycles of uniform weight. Okay? You can check that easily in the example that can never happen. Because if it would be have a cycle in uniform weight, you would have in one coordinate along one axis you would get a loop. So that's impossible. Right. And this is a larger operad. So there will be a map of operads from Gn to Gnx. Okay? A map of operads means for every A you have a map of partially ordered sets, and it respects the composition and the other structure that you have, the symmetries, the permutations of A, and so on. The things that I didn't talk about in detail. So this was first observed by Rainer Vogt and his collaborators, Fjodorovic and others, that you needed this larger operad. However, nowhere in the literature it was explained that these two are equivalent, and in fact nobody knew. So that was the achievement of my student Boykelman, that he found a very nice combinatorial proof that these two operads are equivalent. And in fact it's quite tricky. You have to look at so you use Quillen's theorem A for those of you who know what that means. So you take something here and you look at all the guys here that are smaller, and this thing will have a cycle, be it not of uniform weight, and you do some induction on some kind of size of this cycle. The size has to do with the length and the weights occurring. You had a question?
Yeah, what does equivalence mean here? You realize faucet as
yes. Yeah, so this means that from, yeah, so this is, let me write it down, because I will use this all the time. So this is an equivalence. i.e., if you take Gn of A and you take Gnx of A and you take, these are posets, you take the geometric realization That means you first take the nerve and then you take the classifying space of the poset, or first the nerve and then the geometric realization, that this is a homotopy equivalence, or a weak homotopy equivalence is the same in this case. Okay? For each A. So that's the first little fact. So now, but I'm on my way to try to prove that Gn is an En operad, that it's equivalent to Cn. So how do we go about? So I've explained it almost. You have to go to the larger Gn next. But there is another thing. You see, if I'm going to do a substitution, A is not separated from B in the left-hand coordinate. But if I substitute in A and I put some little disks here, the result may be separated from B. Okay, if I drew it correctly. So in fact, the weight can go down if you substitute. So what this means is that if we have this map, so we have a map. We do have a map. Cn to, I think I call it phi, to Gn x, but it is lax in the sense that phi of, if you have a configuration C of, so this is C here, but this whole thing is, C is a configuration of lots of little cubes indexed by A, and I substitute for a little A another one, then the separation may go down compared to what I do here. Because here I have to keep the same weights. Here is a weight between A and B, that's this one here, and if I substitute I have to keep the same weights, okay? But the separation may be better. So I have a lax map. Now, I'm not going to say too much about this, but this is rather innocent when it comes to comparing operads, because what you can do, any lax map can be replaced by a zigzag of true maps. That's something that maybe you know if you're used to two categories or pseudo categories, and it's not hard to do. So this is innocent, this is harmless, because a lax map P to Q can be replaced by a true map, by a zigzag of true maps P primed Q, where this is an equivalence. Meaning, I'm still in posets, meaning again, it induces a homotopy equivalence on classifying spaces for each set A. Okay, so I'm free to work with lax maps. So that's one gain that I've made. Okay, so now we are a little bit more flexible, and the way that you can prove that Gn is an En operad now goes as follows. We have Cn here. I'm going to write a diagram and I will probably keep it on the board. It maps to Gnx. Here we have Gn. So I didn't explain to you, but I said this is an equivalence. And inside Cn, I just have the configuration space of points. Okay, so conf n of A is the space of configurations of A index families of distinct points in Rn. Should I write that down? Should I repeat it? Conf.
What, the center of the cubes?
Yeah. So here I take well, if you take the center of the cubes, you go this way. Mm-hmm. And if you take a configuration and you take small enough cubes around them, so that, for example, in the standard way, so that they're just about separated, you go the other way. So this is also a homotopy equivalence, because we talked about the fact yesterday that you can always shrink and or expand the size of the cubes. That's less important. So conf n of A inside R to the n to the A configurations of distinct points. Okay. Now this is a bit of a so this we call phi, and now we call in paper we call this psi. This is a bit of a funny diagram. Okay, it's extremely hybrid. This is a true operad in spaces. This is an operad in posets. This is an operad in posets. This is just what is called a symmetric sequence of spaces. For each A, for each capital A, I have a space. And the symmetric groups act, but I cannot compose. I can substitute cubes inside cubes, but I cannot substitute points in points. So another way to solve this problem is here, where you construct a compactification by allowing points to collide. So that operad will play an important role tomorrow, and I hope towards the end of the talk to say a little bit more about it.
First one was in complex.
Right,
Case,
yeah. So this is a real variant of it. Correct. Okay, where were we? So hybrid square. So let me emphasize this. So this is a symmetric. Oh, this is not a pen. Symmetric sequence. Operad. This whole row is in spaces. This row is in posets. And this is just a map of symmetric sequences, and this is a lax morphism of operads. Okay, so I've got rather moved out of my category of little n cubes. So I told you a little bit about how to deal with a lax, the notion of a lax map. So there's one other thing, namely, what do we do for a map between a space and a poset? And mind you, I didn't say anything about continuity or something, right? It's just a map from a space to a poset. And one of the strange things is, well, surprising things is that this doesn't seem to play a role. And what is going on, and maybe I will write it here, although we shouldn't forget this list at some point. So, if x to p, let's call it phi again, is a map from a space to a poset, we can construct a zigzag x xp p, so a zigzag of spaces. So p, absolute values, I already told you but didn't write it down, is the realization of the nerve of p, and x sub p is something like it. So xp is the realization of the simplicial set whose with n simplices you take something in the nerve of p that looks like this, and you pick a point.
Have lines around that. So XP is the realization.
Thank you. Of the simplicial set xp, whose n simplices are of this form, and you take an x, and you ask that phi of x is less than or equal to P0. Okay? So, and then this is always a homotopy equivalence. Because this is also the nerve of a poset, and this nerve of the poset, if you're used to this sort of thing, this nerve of the poset is, as a category, it can be contracted to the X as a category with as a discrete category. Okay, so this is always a weak equivalence. So you can view this guy here as some sort of generalized map from X to P in the homotopy category, from X to the classifying space in P. Yeah? So
Space structure doesn't play any role.
apparently not, but I will in the proof that I'm about to sketch, it will come up in the following way. I would like this to be a weak equivalence also, and for this I would have to know. Well, one way to figure this out is to show that these x's, which are all whose phi image is all below who's a given P0, form a contractible set, and the CW complex. Yeah. So the right hand side also xp to P is a weak equivalence if each I call it, what do I call it? Each down P is x such that 5x is less than or equal to P is a contractible CW complex. Okay, that condition is a bit stronger than necessary, but this will do for the purposes. Okay, so it's really saying that this guy is a model for the homotopy co-limit. If you ask it to be these things to be CW complexes, and then if they're all contractible, then it's also the homotopy co-limit over P of the diagram, which just consists of a point, and then so that's quite a standard thing. Yeah. Another way to think of this map is that you have a stratification of the space X. Yeah? There's also a common language for this. Stratification, whose strata are indexed by the elements of the partial ordered set P, and the inclusion relations are given by the poset structure of P. So it's also about it's also something about stratified spaces, which maybe also explains the question about continuity or the relation between the poset structure and the topology of X. Okay, very good. So you can interpret this diagram in this way. Now, what I'm going to at least give you the idea of the fact that this map psi is an equivalence, meaning that for each set A, it's weak homotopy equivalence, and then we are done because we have this funny diagram, but we at least have one good map here, almost a good map, a Lex map of operads. Okay. So the fact that Cn is indeed an En operand now follows
GN, don't we know about
Gn, thank you, follows if we show that each conv and A to, well, I want to say GNA, but let me put it in quotes because it's like this thing there from a space to a poset is a weak equivalence, weak homotopy equivalence. Yeah, more precisely, in the notation on the left hand top. Sorry. Conv n A and then I put the poset as a sub-index, so this is my P, and it maps to the classifying space of this partially ordered set. And this is always a weak equivalence, more precisely in the right-hand side is. Okay? Okay, so this approach is quite different from what was earlier in the literature, and how to prove this is also quite different, but we use well, a trick or an insight of Kashiwabara that he used in quite a different context, and it's sort of funny to see how this works. So I want to explain that to you. Let me leave this for a minute. It's important. Okay, this can also go.
Sorry, sign is
Yes.
kind of the same naive map by
Yes, I'm
comparing
sorry,
by
that's a very good point.
but the-
Yes, I'm sorry. So it's defined in exactly the same way, but then you compare points and you look at the first coordinate in which they are separated. I should have said that. And then you can actually check that it lands in Gn and not in Gn next. Yeah, and that's quite also completely elementary. I should have said that. Thank you. Right. So I want to analyze this diagram. Okay. So this is something on the set A. And I'm going to prove this by induction on A. So this can be proved. Induction on A.
On the size of A.
Okay. If A has one element, you can all check it for yourselves. If it's true for A and if it's true for B, to keep the notation of my notes, and I add one element to B, then it will follow from if I know it for B. Okay? So the induction step is where A is B union a new element A. And now I'm going to look at these maps. So I have, so if you're taking notes, leave some space above. Conf and which was the larger? A. I'm not going to copy the thing in the middle. GNA B GNA. So you have a diagram like this, and these maps will have fibers. More precisely, they will have homotopy fibers. So you turn the map into a fibration and you take the fiber. Homotopy fiber is something for which you have the long exact homotopy sequence. Now, this guy here is a very well-known fibration. It's the Fadel-Neuwirth fibration. Okay? And its fiber, if you have a configuration of a B-index family of points in Rn, and you want to add another point to it, a point indexed by this little a, it has to stay. It has to stay a configuration of distinct points. So you have to stay away from the B index family that you have already. So you have Rn minus B points. Yeah. Rn. So over the fiber, let's take a point x is xb b in B here. Rn minus xb b in B. Okay, that's a wedge of spheres. indexed by B up to homotopy. Okay. So you take the sphere around the points that you have deleted, and that gives the homotopy equivalence. Or maybe, strictly speaking, I should write it like this. So that's a fibration. Now, we know that these things are equivalences. That's this equivalence here. So the fibers will be equivalent. Here I will get something similar. I could write it exactly in this model. You make a realization of a specific simplicial space, but it's not so important. I said simplicial set, but I should say simplicial space because X is a topology. Right. Now what about this side? How can you prove that such a thing is a fibration, at least up to homotopy? Well, there is a very famous tool for this, which is Quillen theorem B. So the right-hand side is a fibration up to homotopy by Quillen theorem B. Okay?
You mean you can compute the fiber with your...
Okay. This is not Quillen theorem B doesn't give you this. I have to do some work.
Yeah.
Okay? So I will do the work. And I will do the work at least in an example. So what does Quillen theorem B say? So let me go here. Quillen theorem B really works at the level of categories, in particular posets. Okay? So I have this map of posets from Gn of A to Gn of B. And I fix a particular graph G. Okay, these are the graphs where you have one extra point, and this maybe is it's called row in the paper, I think. You look at all the elements here whose row image, I think if you forget the point A, land below G. So that's written row over G. So that's the poset of H's such that row of H is less than or equal to G. Okay? Now, what Quillen theorem B says is that you have to check that this thing, the homotopy type of this thing, does not vary if you change G. If you move from G to a larger G primed. Okay? And then, to prove that this is an equivalence, you have to check that here also you get a wedge of spheres. Okay? So the claim is rho over G does not change with G. Okay, I gave you a more precise statement in words. If you go from G to a larger G primed, you get a map from rho over G to rho over G primed. And if you take the classifying space of this map, it's a weak homotopy equivalence. Okay, is that clear? Okay, i.e. and rho over G is again a wedge of spheres. Yeah? And moreover, this map, I will not be explicit about this, will actually give this equivalence from this wedge of spheres to this wedge of spheres. That's also something you have to check. Okay? The equivalence goes by the right map. Okay, now to check this is sort of fun, and I will explain to you in a very small example. Okay? So let's do the example maybe here. But the example completely illustrates what's going on. So let's take for G, let's take for B 2 points. Let's take for the weights just 1 and 2. So n equals 2. And let's put an arbitrary weight here. Say 1. It will not play a role in the argument. Okay? Now I have to look at all the graphs that are smaller than where I add an extra point little a. And if I forget this point, I get below this one. Now I put a 1 here, I cannot go any further down. So there are 3 possibilities. So a can be, since it is a linear order, I'm in G, right? I'm not in Gx. Oh, sorry, that's black. So B1, B2, B1, B2, B1, B2. I can add my A here. And I can add my A here. Or I can add my A here. Okay? So if I have a graph such that I forget the point A, I land below this one, it has to be one of these 3. Okay? But with weights. Now the maximal weight is 2. So if I put 2 here, then I have to be below one of these 3. Okay? So if we call this G0, G1 and G2, then I know that rho over G, so this is my G, is you have to be below G0, or you have to be below G1, or you have to be below G2. Okay? It's very simple. Now, these are posets with a maximal element, so they're contractible pieces. So I know that rho over G, the realization, is a union of 3 contractible pieces. Now, how are these contractible pieces glued together? So let's look at the intersection. Yeah? Let's look at rho down G0 intersecting down G1. I'm sorry, I'm standing slightly in front of it. So if you have something, if you have a graph which is below this one, as well as below this one, something has to happen in the direction of the map from B1 to A, or A to B1. Okay? So the weight has to go down, because either with compared to G0 or to compare to G1, the direction will be wrong, so to say. So this is down. Let me try to copy it. B1, B2. I didn't get this way, it doesn't matter. A, 1, 2. Union, down, B1, B2. Where is A? A, 1, 2. Okay? Are you with me? Okay. Now these are again 2 contractible pieces. So the union of, this is a union of 2 contractible pieces whose intersection consists of 2 contractible pieces. Now you play the same game. What is the intersection of this one and this one? If it has to be below this one as well as below this one, then the weight on the edge between B1 and A has to go down, because the direction will be wrong in one of the 2 cases. But it cannot go down any further, because 1 is the minimal weight. So these 2 are disjoint. Okay? So this union here is 2 contractible pieces whose intersection is 2 contractible pieces that are disjoint. That's a circle. Okay? And you do the same thing here, and you can check, you get a wedge of 2 circles. Okay? The 2 because of B1 and B2, the circle because I took the weights 1 and 2. So I'm in R2. It's a wedge of spheres in R2. Okay? Now, this argument, it works in any dimension. You have to be a little bit more careful about indexing and intersecting and seeing what is going on and so on. But you can see that this is a wedge of spheres. Now, this is not yet equivalent theorem B. because I have to check that a certain map from what I know is a wedge of spheres to what I know is a wedge of spheres is a weak equivalence. But what happens if I change this graph in B? Perhaps the linear order changes. Because I haven't used the weights here. Linear order may change. So the way I attach these cells may occur in a different order. So the map, this comparison map, is just a permutation of the wedge. These spheres in the wedge, and you permute them a little bit. Yeah? According to the order, this wedge occurs in the order of the linear order of the graph. This graph. Yeah. So that's what's going on, and you can also check, what I will not do it, that this is a weak equivalence by using this criterion that I wrote down about contractible CW complexes, because these contractible CW complexes will just be spaces in Rn where you cut out some slices, but they sort of, you can explicitly see what they are, and they're obviously contractible. So that's the proof. And I think it's a very nice argument, and it's a mystery to me that the literature was a little bit messy. I have until 3, more or less. Where's the boss? Yeah. Okay. So I will say a few things also in preparation of tomorrow's talk, but I wanted to show you at least one real proof using various methods of sort of classical algebraic topology and the interplay between categories, posets, topology, and so on. Now, I started my lecture by saying that this notion of En operad can hardly be called a notion philosophically, okay, because it's a notion by example. Yeah? The notion of a white swan is a swan that is similar to this particular white swan. That's very strange. Now, what seems to be going on is that this operad Gn plays a very central role in comparing other operads. So I made this list, which is no longer there. But, for example, to prove that this McClure-Smith operad is an En operad, you again construct a map which is a little like the map from Cn to Gnx. You construct a map to the graph operad. For these iterated monoidal categories, you can do something similar. There is quite a canonical map to the graph operad, so it seems to play a central role. And maybe it gives a hint to what could be the notion of an En operad. But that's a very vague statement because I have no idea how to distill some properties that are characteristic of this. Now the question?
Yeah, I'm asking what model of definition. I mean, you have other operads which is defined without a model that you want to imitate or what? I mean, can you give an example of operad that you define without being equivalent to a given one? Any other operad?
For instance, operad of endomorphism of something.
Endomorphism is a good
Thank you.
That's right.
Saved by the
So
bell.
you want this to be endomorphism of something?
No, I don't know. Structural properties. What are the
Yeah.
structural properties that make an operad an En operad? Huh?
Property. You want to define it by property.
Yeah.
Like
Like
one operaad you could do say
Yeah.
it's contractible.
Like you want, yes.
Yeah.
Doesn't the correct definition include a multilinear map from a number of E1s to it, which is a sort of connected to description in terms
Yeah.
of the
So now this is a little bit of a dangerous territory because now we are entering into possible guesses and properties and structure that we might add, and we will easily run out of time. So I will be very happy to continue this discussion, but let me first finish the
I
lecture.
understand.
There was a question from the online audience. Any reference for the realization of rho over G?
Yeah, it's in this. So I have a paper with Boykelman on the archive. This is this paper. I will write it down. a small catalog of
We
En.
can't see the green. So
Yeah,
it's
I'm
okay.
writing it
Okay.
Okay. A small catalog of En operads. I have written a lot in green already,
Yeah.
and only now you tell me.
Blue is better.
Yeah, there was one blue thing that didn't have. Okay. So you didn't follow this little calculation with the.
We do.
No,
but
we
I think
do.
online.
No, it's,
On-
it's okay. It's,
We see the green.
Oh, okay.
Some
So I would like to say a few things about this Fulton-McPherson operad. Not green. So background for tomorrow. That's not good.
Just give me this stuff.
Background for tomorrow. So we have this Cn of A, and we could take the centers of the cubes, or we could enlarge points to little cubes to get a configuration space, conf n of A. Okay, and this Fulton-McPherson Fm n of A is a compactification of this space. Now, a compactification of a space, you add a boundary. This is a manifold. It has a dimension of dimension n times A. But it is convenient to make this space a little bit smaller in a relatively innocent way. So I look at configurations, modulo dilation and translation. Yeah? And I call it n conf A. So it's quotient, it's configurations, modulo, translation, and dilation. So there's a group acting, which is the semi-direct product of translation, R to the n, yes, and dilation. Okay, so it's a contractible group, and it acts freely. So this is just a bundle, principal bundle, in fact. Also, it has a section because any configuration has a sort of normalization. That's why I wrote the n here. You can always say, for example, the barycenter is at the origin and the diameter is 1. So something like this. There are many ways to do it. Okay, so this is okay. And now you can compactify this in a certain way. And for example, there's a well-known paper by Kontsevich and Soibelman where they give nice formulas for how to do this. But what it comes down to is that you allow configurations to collide. Yeah? And for example, if you have a configuration of 3 points, these 2 points can collide together. Yeah? And you could also say this point wanders off to infinity. That's another point in the boundary. But if you normalize, these 2 points colliding is the same as this point wandering off to infinity. Okay, so you can it's enough to only talk about collisions. So this, if they don't collide, this would be pictured by a corolla. And if these two collide, so let's say it converges to something like this, then you picture this configuration, this type of collision by a tree. Okay, and in fact, this space, this Fulton-McPherson compactification, has strata, which are given by trees whose leaves are with A a set of leaves. Okay, here A is a set of 3 points. Here you have a tree with A leaves. This is the interior. It's a manifold. And the boundary consists of trees with at least one inner edge. Okay? And you can have collisions of collisions. Of collisions, right? If you have 4 points, you can have that these two converge, these three converge. But then if you look closely, these two converge at a faster rate, so to speak. Okay, so there would be a tree, and these are the kinds of trees that I've drawn yesterday also. Okay, so the strata by trees. Yeah. And you can use these trees. So I'm not going to do that because I'm running out of time. But you can. Okay, so let me say a few things. The vertices of these trees, if you have a point here, it is given by a tree and an ordinary configuration assigned to each vertex. But now a configuration not of the set A, but of the set of inputs of the vertex. So here you have a configuration of 3 points. Here you have a configuration of 2 points, which is this collided thick point and this point. And here you have the configuration of 2 points, which is this microscopic point, and so on. Okay, and you can use this idea to relate it. So we know how to assign to a configuration a graph. So from the Fulton-McPherson compactification, you can go to trees whose vertices are indexed not by configurations but by graphs. Okay, and that is a standard resolution of this operad GN. I said yesterday the Stashev polytopes can be identified with the Boardman-Vogt resolution of the associative operad. These trees whose vertices are labeled by graphs can be identified with the Boardman-Vogt resolution of this operad. So you have something homotopy equivalent to GN, and that's one way to prove that Fulton-McPherson is also an EN operad. But that's extremely sketchy, but that's how we do it in the paper. Tomorrow, I will use a few properties of this Fulton-McPherson operad. I will use that this is a manifold of dimension, what is it? N times A minus N minus 1. And I will use that this is a manifold with boundary. So for a manifold with boundary, the homotopy type of the complete manifold, the compactified manifold, is the same as that of the interior, because you can build a collar around the boundary and sort of contract the whole thing into the boundary, intuitively speaking. So that's what I'm going to use, and I'm going to use that this boundary is parameterized by trees with at least one inner edge. So try to remember these. I will repeat them tomorrow. And I'm going to use it to prove a theorem due to, well, the version I'm going to give is due to Guppel, as a PhD student of Michael Weiss, where he proves a bound on the connectivity of I was going to be a complicated sentence. A bound on the connectivity of the derived mapping space from one EN operad to another EM operad. Okay, and it's again, it makes use of all the analysis of trees and maps between trees and so on, and it's very nice combinatorial proof. And for those of you who will not be there tomorrow, it uses very heavily truncation of operads, operations with at most n inputs, or trees where the vertices have at most n inputs for varying n. Okay, so that's the main technique. It's a little bit like building a Postnikov tower, if that means something to you. So thank you very much.
Any questions?
So fine, so tomorrow everything will be all integers or all cells, so it will be the equivalence of topology spaces, right? So no rational models.
No. I will make a remark about this tomorrow as well. Yeah. No rational models. Yeah.
No rational, and then the second question is, so I'm a person from the rational models, and I'm interested
algebras over this operator.
Yeah, so you no, I haven't thought about this, but I see what you mean. So if you have the configuration space of a manifold and you have a way of, I'm sort of repeating what you say. You have a way of, you have coordinates.
So my person,
Yeah.
multiplication of
Yeah.
configurations of points.
Yeah, but you want it to be a module for the en operand, right? Yeah. So you need to define this action. Yeah.
Yeah, I wanted the action of En.
Yeah.
So to define this action is very simple because if you look not on the points but the small disks on the manifold, then you can substitute inside the disk the
Yeah, but you need, that's what I was going to say. You need some structure on the manifold to know what the disk is. You need a Riemannian metric
For
or
example,
something like that.
Riemannian
Yeah.
parallelizable manifold.
Yeah, exactly. That's what I was going to say. Yeah.
But for those you have such construction.
No, I haven't thought about it. No.
For the stash of pentagon,
Yeah.
you add this stratification. So the boundary is really, is it the same boundary as you're talking about here? So each point of the stash of thing.
Yeah, the
corresponds
interior of the, that's correct. The interior of the polytope.
is
Well, it's a bit more. You have to think about how to parameterize this. So
isn't it by length of the edges?
yeah. So I divided the pentagon into squares, and the square was defined by this tree with two inner vertices, two inner edges. Sorry, that I put in the middle of this edge of the pentagon. Okay, and if you assign a parameter, a length parameter to these edges, and you say if the length is 0, I contract the edge. Then if you take one of the edges, you make them 0, you go to the old vertices of the pentagon. If you make them both 0, you go to the center. So that's how you parameterize it. So okay, so the interior, it's not exactly true that it is that corresponds to the corolla. It's a little bit more subtle. But the parameterization is completely explicit. Yeah.
Any questions? Okay, so let's thank the speaker again. And our last talk is tomorrow at 11.